this evening we're going to do a little bit of a preamble and an investigation around inductance and coil. Yeah, we're going to start off by looking at doing an investigation of DC and AC current into a coil, an inductor. Alright, for the benefit of this experimental one, I'm just going to use a coil cable with good things open. That's an inductor, but there's a coil. Okay, what we're going to do is use a meter to measure the resistance to the coil. Yeah, and then we're going to apply a DC voltage and by Ohm's law think what the expected current is and then measure it. Okay, so the expected current will be calculated from the measured resistance and the applied voltage, and then we're going to measure the current. We're going to do the similar thing with an AC voltage, apply an AC voltage, by Ohm's law what we expect it to be, the current, and then what it actually is. Okay, and then from there we'll go on to discuss why we get the results that we get. Okay, so I'll pause the old read there. So, having done all of that, taken those measurements, we got 6.8 ohms was the resistance measured with an ohm meter. We applied 6 volts DC. We said we were going to get 0.88 of an amp via Ohm's law, and we got 0.87 of an amp practically. Off we went to our AC power supply, measured the voltage, 6.7 volts, used Ohm's law with 6.8 ohms, predicted 0.99 of an amp. You might well think that'd be right. Yeah. When we actually turned on the ammeter, we got 0.53 of an amp instead. What's going on? Because they're saying Norfolk. What the heck is going on? Yeah? So, what we need to do is try and explain that through the theory around coils and inductance. Okay? So, electromagnetic induction. 2 laws govern electromagnetic induction. Faraday's law. A voltage is induced in a circuit whenever relative motion exists between a conductor and a magnetic field, and that the magnitude of this voltage is proportional to the rate of change of flux. So if we had a coil like this, any coil, and we get a magnet, I haven't got it here to demonstrate, but move a magnet in the vicinity of that coil, so the lines cut across the conductor will induce a voltage into the coil, and if there's a closed circuit, a current. Yep. So that's first law, that's Faraday's law. Relative movement between a magnetic field and a conductor causes an induced voltage. Lenz's law states that the direction of an induced EMF is such that it will always oppose the change that's causing it. Yeah? So it becomes an extra resistance to current flow. Because we got this change in current, or change in magnetic field, the voltage induced is going to be in a direction such that it tries to oppose that induction. Provide some resistance to it. Okay? So, on the next slide, if we pass a DC current through a coil, yeah, produces a magnetic flux such that that magnetic flux looks like what you would get. You must remember the bar magnet and iron filings from school. It looks like the magnetic field on a bar magnet. It will have a north pole and a south pole depending on the direction of current. If we reverse the current direction, the north will go on the left hand end and the south the right hand end. Yeah? The flux form an overall field with a north and south pole similar to a permanent magnet. Strength of this field can be increased by one of three things. Increasing the number of turns in the coil. 2, increasing the current flow. And 3, adding a ferrous core, because then it better supports the field. Much happier in an iron core than it is in air, for instance. Okay? So the stronger, more iron you get in that core there, the better the field and such like. Okay? So that's what happens when you connect DC. So looking at that in sense of this, Michael Faraday discovered that if a magnet was moved in and out of a coil, it induced an electromotive force, EMF, or voltage across the coil, and therefore a current was produced. So, what he's saying is that he found that if he moved this north pole into that current loop, you'd see a deflection on this meter. And the faster you moved it, the more deflection. Okay? If you stop the movement, no relative movement, remember I said relative movement in Faraday's law, the current disappears. There must be change for induction. If you then pull the north pole out in the opposite direction, you'd get a deflection that way. If you turn the magnet round, you'd start off by putting the south pole in, you start off with a deflection to the right and then go with a deflection to the left. So you'd effectively change the direction of the current over. Okay? Again, another point to note is the EMF, it's a relative motion between the two. So if we keep the magnet still and move the coil, we'll get a similar effect. Yeah. And again, we can add more turns to the coil, we'll get more current, increase the field strength of the magnet, we'll get more induction, and moving the magnet or coil faster will give us more. Alright? Now, if we take a simple inductor coil in an AC circuit, as the supply voltage increases and decreases, an EMF is self-induced across the coil. So as in 1/2 cycle, we've got a change in voltage, therefore a change in current in that coil. We get a voltage induced in that coil. But by Lenz's law, that EMF opposes, so it's trying to push a current in the opposite direction. I induced. It's never as big as that one, right? But it's trying to do that. And then in the other half cycle, the natural current would be that way, and the induced by Lenz's law would be that there. And the point where there's the most induced EMF is here, where the rate of change is highest, and the point where there's no induced EMF at the two peaks, because the current isn't changing at those, it's stationary. Remember, relative difference, it's change that's going to cause this. Okay? So, the applied current is in the direction as shown, the induced current is opposite to it. Not as big, okay, but the faster that movement, the more there is. So another way to imagine this is, as the AC current is changing every half cycle, as building up a field in one direction, collapsing it in the other direction and building up opposite, and collapsing away again. So all the time there's this induced back EMF, think of it, that's going to cause extra restriction to current flow. Because if we've got 1 amp normal current and half an amp back current, we're only going to have overall half an amp flowing. Yep. So that's why we don't get the current flow on AC that we expected, because of this Lenz's law current, the back EMF causing the back current in the coil. Alright? What, happy with that so far?
Yes, as I thought.
Yeah.
The waveform.
So, AC inductor phasor diagram. The blue line, okay, is the voltage. Because of this inductor current being caused to go, the inductor current is the induced current, ends up 90 degrees out of phase, because, like I said, the maximum current is where we change over the x-axis. The minimum current is where the voltage is at the peak. So if you could have a pure inductor that only had inductance and no resistance, not possible to get one, because even a coil of cable's got resistance, okay, you'd be exactly 90 degrees out of phase. Yeah? So we can express that when the applied voltage is a positive or negative peak, the rate of change of current is nothing, hence no current induced. When the applied voltage crosses zero, rate of change is maximum, hence the maximum current is induced. This means for a pure inductance, current lags the voltage by 90 degrees. So here's our voltage phasor, there in red, and there's the current phasor, 90 degrees negative. It's behind or after voltage in time, because these are angles here, but that can also be time in seconds, and the current peaks 90 degrees after the voltage. It lags it. Yeah? So, what we need, what we can do to help consider that in calculations is the inductive reactance of a coil. The opposition to current flow in a pure inductance is called its inductive reactance. Has the symbol X subscript L for inductive reactance. You have the subscript because you can also get capacitive reactance. Alright, we haven't come across that yet. It's XL. It's also measured like resistance in ohms. Yeah? Because the induced EMF and current will be greater if the applied voltage changes faster, the magnitude of the inductive reactance is dependent on the frequency of the applied AC. Because if we change things faster, the back EMF gets bigger, so the back current gets bigger. Therefore, relatively, it must be because the inductive reactance has increased. Yeah? So we calculate inductive reactance from the formula XL as equal to 2 pi times the frequency times the inductance in henries. So from that formula you can see, if I increase the frequency, XL is going to get bigger. If I decrease the frequency, it's going to get smaller. Yeah? Okay? This means the frequency increases, the reactance will increase, the current will decrease, because Ohm's law can be applied in terms here. The inductor current is the voltage divided by the inductive reactance. That formula only applies for a pure inductance, or just looking at the inductive part of the current. Okay?
And in AC.
And an AC. Now, impedance of a real coil. So, it's not realistic to have pure inductance. A real coil can never be a pure inductor because the wire of the coil will have a DC resistance. That's what we measured. 6.8 ohms, I think it was, wasn't it? Yeah? A real coil can be represented as an inductor in series with its resistance. The resistance of the inductor does not change with frequency, but the reactance does. This leads to a different term being used to describe the opposition to current in an AC circuit. Instead of resistance, we use a term called impedance. You must have heard of that before, Dan, yeah?
Yes, in car speakers.
Okay, you will have done in car speakers. Anything to do with hi-fi, yeah? They got an impedance. The amplifier output's got an impedance as well, alright?
Yeah.
So the circuit symbol for impedance is Z, and the impedance is also measured in ohms. So it's getting confusing now. We've got three things already measured in ohms. They're all different. Resistance, inductive reactance, impedance. Okay? The key thing is impedance is a vector quantity. It's got direction and size. Okay? Note for DC current, a frequency F is equal to 0 and hence XL is equal to 0 ohms. So we take the frequency away, we take AC away, and make frequency equal to 0, 2 pi times 0 times L equals 0. Yep? No XL at all, just pure resistance. So that's why in DC we got the current we expected.
Obviously in electrics you have group impedance. It's always ZE or ZS.
Yeah, that's important that where you, because that's intended as an AC circuit, you even call a resistance an impedance. It's an impedance with no angle associated with it. Yeah? Or zero angle associated with it.
You have to have voltage, I guess, to measure the hertz and frequency to work that out. Yeah.
So, we come to the main part. The impedance of a real inductor is a vector or phasor made out of the resistance of the coil and the reactance of the coil. The inductance of the coil creates a current that's 90 degrees out of phase with the applied voltage. This means the reactance has to be represented 90 degrees out of phase with the resistance. So XL, we've got a line down the bottom here representing R. It is at 0 degrees, horizontal, left to right. And then XL is 90 degrees, as a positive 90 degrees angle for XL. And that's something you can only remember. You should remember that. XL, inductive reactance, is a positive reactance, upwards, at 90 degrees. Then, our impedance, the overall combination of that resistance and that XL, is to complete the parallelogram here so that we got a phasor Z ohms at angle alpha in there. So if we wanted to, if we know R and we know XL, we can use Pythagoras' theorem to calculate Z. Equally, if we know Z and we know R, we can use Pythagoras' theorem to calculate XL. Alright? Okay with that, Dan?
Yes.
Yeah? So, it's important to point to remember that impedance triangle. And later on, 2 weeks' time, we'll bring in capacitive reactance as well. So, you get the combination of all three. Alright? So, impedance varying with frequency. If we have DC, no frequency, there's no XL part, and therefore impedance and resistance are in line with each other and they have the same value. Yep? At lower frequencies, XL is relatively small, and R's there, and we've got an impedance there, Z. If we increase frequency, the XL line gets bigger, the R line stays the same length. Therefore, this angle must have increased, alpha is bigger, and therefore this Z line is longer. So the impedance has increased, okay? There's a phase angle change and the current will get reduced. So as we increase frequency in an AC inductor, the overall impedance is going to increase. If we decrease frequency, overall impedance is going to go down. Yeah? Okay? It's important to remember that the value of a resistive ohms doesn't change, and that's why the angle changes, because that's held stationary, but this line is getting longer or shorter, the XL line. Okay? We're coming to that in a minute. We're going to work out L in Henrys for that coil we measured. And that's part of your assignment, practical work as well. As you'll see through. Right? Find the inductance L of the coil from the beginning of the session. Yeah? So, how are we going to do that? What do we know? We know R, don't we? What was that? Let's have the measured value when we pass DC current. The practical value.
Oh, that was 6.8 resistance.
Yeah, but we measured it with a meter initially, and then we measured it with an ohm meter, but then we calculated it using Ohm's law from the voltage applied and the current. No, not current, ohms.
6.8 ohm.
Yeah.
The resistance of the coil was 6.8.
Yeah, measured with. And what I'm saying is, we measured it with an ohm meter.
Yes.
Oh yeah, and then we used. Yes, sorry. Yeah. Okay. Anything else on there that we've got from the practical? What else have we got? Have we got, what was VDC?
6.
6 watts. 6.0. Yeah? What was IDC?
0.87.
Yeah? What was VAC? And IAC? Right. This is what I meant. Let's just take this away for a minute. From the practical results, from DC practical results, R is equal to VDC over IDC, which was 6.0 divided by 0.87 equals. What is it?
Yes.
What is it? Yeah, 6.9 ohms. Not quite what we measured with the ohm meter. Right?
We worked it backwards.
Worked it from the practical results. They're going to both be practical results. What can we work out from the AC practical results? What term is the overall opposition to current in AC?
Resistance. Resistance current.
Measured in ohms. Overall opposition to current in
The
AC
inductive
is
resistance.
impedance. Yeah? Just go back where we first introduced impedance. Impedance of a real coil leads to different term being used to describe the opposition to current in AC circuit. Impedance. So the overall combined of resistance and reactance is called the impedance. Yeah? So, going back again to our last slide, we can calculate the length of that line, the Z line, using the AC results. Z is equal to VAC divided by IAC. That is
12.64.
6.7
Divided by
divided by 0.53 equals.
12.64.
So let's do 12.6 ohms. Yeah? So we now know that length of this line is 12.6 ohms. What can we now calculate? We've got two sides to a triangle, right angle triangle. Calculate the third, which is this height of XL up here, can't we? Yeah. So we can do 5 Pythagoras XL is equal to the square root of Z squared minus R squared. That's Pythagoras rearranged. You alright with that, or do you want me to show you how it rearranges to that?
I'm okay with that.
Yeah?
Because it should be XL by XL. To get
The original version is Z is equal to the square root of R squared plus XL squared. Yeah, and you just take away the square the other side, and that ends up Z squared minus the other side. Yeah? Okay, so we can put the numbers in. So square root of Z squared, which is 12.6 squared, minus R squared, which is 6.9 squared. Do the math. And what is that? 104.25 ohms. That seemed a bit high to me. There's 144. That's about 144. That's about 49. So there's 180 square rooted. Square root 180 in 100 and something. So we're talking about square root of 12.6 squared. That must be less than 12.
10.54.
Plus 6.9 squared equals. I get 14 point something. Oh, I'll put plus in instead of minus. That's better. 10.5. Ohms. Has to be less than the length of the hypotenuse, doesn't it? Which is the Z, the 12.6. Looking at the triangle,
Yeah.
right, the Z's got to be the biggest. Yeah, so it has to be less than that. Yeah. Also, XL is equal to 2 pi FL. F is equal to 50 Hertz because we're using low voltage off the mains. Okay, we can rearrange that to say therefore the inductance L is equal to XL over 2 pi F, which is 10.5 divided by 2 times pi times 50 equals.
Naught point naught
0.03 Henries equals 30 millihenries. So that coil's got an inductance of 30 millihenries. And that's a well-known method of being able to practically find the inductance of a coil. And I tell you, that ain't far off what a £2,000 inductance meter that Chris has got hid away somewhere. I'll find, put that on it. That's pretty reliable because you're passing quite a bit of current, so the measurements are quite reliable. Yeah. All right with that, Dan?
Yes.
Yeah.
Mm.